Anything to add, or is it?
No, that's about right. Except I preferred the word continuous delivery to DevOps, but apart from that, it's good.
Okay. Well, that's how the book was called, I think. Mark Richard, author of a number of O'Reilly books on microservices, messaging, founder of developer2architect.com, which is a website that is intended to help developers grow as a software architects, right? That's perfect. Tomorrow, Mark will be running software architecture, the hard parts training, and I think there are a few spots still available. That's a question to Katharina mostly, but
I hope so.
So do I. Len Bass, you've heard Len's presentation. Len started his professional career when I was personally at the level of architecting Lego bricks. And his book of software architecture in practice was foundation of my master's thesis. So that kind of shows the experience of Len, which I am extremely excited to have here. And Christian is a software architect here in Appium Hub, right? So my name is Jakub Marchwicki. I am working here as a software engineer in one of the Barcelona companies called Casumo. So I think we can start. Before we get into hard questions, there's a question to you as an audience. By show of hands, we would like to know, how do you feel familiar with the concept of reactive architecture? Who of you has heard about the reactive and reactive architecture? Okay. Okay, and who of you did anything in terms of reactive architecture? Has it on production or something like this? Okay, so I think we start with some basics, like the baseline. Because whenever it comes to reactive as a term, we have reactive systems, reactive architectures, reactive programming, probably a few more reactives. Can we make start with a distinction, like what is reactive architecture and how it stands out from what we are having so far?
So the Reactive Manifesto had some definitions about what it was that we're talking about. And at that level, we're talking about architecture and systems rather than reactive programming styles. So a reactive system is responsive. It's resilient, which means that it's responsive in the face of failure. It's elastic, means that it's responsive at different scales as demand changes. It's still responsive. And any one of those, as Mark pointed out earlier in the conversation, any one of those is relatively easy on its own, but a reactive system can do all of those. And one of the ways that kind of underpins that in a reactive system is the use of asynchronous messaging to try and manage and, to my mind, separate the essential complexity of a problem from the accidental complexity of a problem. And that allows us to maintain the responsiveness and the resilience and the elasticity. So as a starting point, that's what I think of it as. And it's very much more an architectural style than a programming technique. So reactive programming and libraries to facilitate that are one kind of thing. But this architectural approach to kind of maintain these more flexible, more dynamic systems, more robust systems is really what we're trying to talk about, I think.
Okay, yeah, Mark?
Also, to kind of further that definition, one of the leverages, I think, of reactive architecture, especially with some of the patterns we're going to be talking about in this panel, is really the creation of autonomic systems. Those are systems that kind of model our human body, systems that are self-aware, systems that are self-configuring, self-protecting, self-healing, self-growing, all without human intervention. We talked in the last panel, had a good discussion about the evolution of software architecture, and I would follow that by saying I think reactive architecture itself is a glimpse of that future. So.
Yeah, so I would like to add, it's more than asynchronous messages. I would argue that it is the separation of the monitoring and the reaction to the information that you're monitoring from the functionality that you're trying to achieve, and that you're looking at an architectural style which really has what is modular in the sense that you can't, in order to be able to scale it, you have to have divided the functionality into scalable pieces. In order to be self-healing, you have to have divided the recognition of problems from the activities that are going on and so on. So I would say that you're talking about a system which is very modular in terms of its different activities.
When we start discussing this debate or kind of preparing, Christian pointed out very, very interesting observation. I don't know, quite Christian, if you mind, but how it then differs, because we talk about modularity, about decomposition of the system, how it differs from what we had in the past that we put on the umbrella of enterprise integration patterns or the, well, SOA. I know there's microservices, the new SOA, but now we have reactive architecture, which is the new SOA. So how it differs from what we already know as a software engineer or as a software architect from the past? Or should we build upon that, or it's like totally different paradigm?
So I think the thing that Mark pointed out is important is that part of being a reactive system is that it's at some level it's sensing the interaction. You know, it's sensing its own behaviour and it's responding to that as well as the interactions with the system. So if it, you know, if the system, as the system comes out under increased demand, it scales out, and you know, we can think of ideas like auto scaling and that sort of stuff. But also in terms of, you know, ideas like, you know, if the system comes under demand, it starts applying back pressure to make sure that the signal is sent and can be responded to in the right place. So it's those sorts of behaviours that I think differentiate this. I think Len's point is important as well in terms of he's talking about the monitorability, but I think it's broader than that. I think if you know, one of the techniques, one of the reasons why I mentioned the importance of asynchronous messaging from my point of view is because what that gives you, it gives you an opportunity to really remove nearly all of the accidental complexity from these little bubbles of behaviour that form the application. And so, you know, in some ways, I'm hoping to make the case that this is actually a simpler environment to work in. It sounds incredibly complicated and difficult, and at some level it is, but actually working in it day to day can be an awful lot simpler if you get it right.
Well, and hopefully now we can get actually a debate going, because in my view of having worked with reactive architecture for, well, past 5 years, 5.5 since the Reactive Manifesto came out. Just as a matter of fact, work I was doing while at IBM, not with Ian. Where's Ian? Oh, Ian. Wherever Ian is. Work I was doing at IBM had to do with the exploration of autonomic systems. I tend to see reactive architecture as orthogonal to other architecture styles, such as service-oriented architecture or microservices or service-based or even event-driven pipeline. I mean, if we talk about all the different kinds of architecture styles that we have, reactive architecture, I don't classify myself as one of those architecture styles, but rather can be implemented through any of those architecture styles. Certainly you can have a service-oriented architecture that doesn't react to its environment, to its conditions, to its errors, to elasticity. Adding reactive architecture to these different kinds of styles gives it that kind of capability to automatically, again, without human intervention, to address these real problems that exist, not only in architecture, but also environment, failing transactions, etc.
So let me go back to Conway's Law. So one of the motivations for service-oriented architecture is that we have different organizations responsible for different services. I find it very difficult to see how I could build a reactive system when I have different organizations with different business goals, with different budgetary constraints, with different everything, and one is monitoring the other. I mean, so I'm disagreeing with you.
Right, and I think with that, actually, Len, all the more reason to actually have reactive systems. You see, when you talk about the distribution of different parts of the system owned by different kinds of parts of the organization, we start to lose a lot of the control and monitoring and stuff of that from a manual human intervention piece. adding some of the reactive architecture patterns, which I'm dying to get into, really helps us observe, as Ian was talking about. Observability is one of the key aspects of reactive architecture. We can't possibly be reactive on any given system if one system is failing. As Dave just said, I can apply back pressure knowing that that system is failing, even though I don't have control over that system. And so I actually would disagree and say that reactive architecture, I think, actually doesn't add the complexity, but actually is a necessary part of bridging those separate pieces together.
Yeah, so I was arguing with the assertion that that reactive architecture is orthogonal to your other architectural choices. And so I was using the SOA as a counterexample. That was kind of the point I was trying to make.
I think I might back that up in that I think it rules out certain other architectural styles. So you can't imagine being able to build a reactive system. So one of the things that's in the Reactive manifesto is asynchronous messaging. I think you can't genuinely build a reactive system with synchronous messaging because they're too tightly coupled. You can't externalize sufficiently, is my own belief, which is why we put asynchronous messaging in as one of the four kind of key principles.
However, you can get the other components like resiliency or elasticity without, or you cannot.
I don't genuinely believe. So one of my friends. So my involvement on the Reactive Manifesto came from working on a particular project where we built one of the world's highest performance financial exchanges, and my friend that I worked alongside with that, Martin Thompson, he says that he thinks that synchronous programming is the crack cocaine of programming. It's kind of stuff that we've all got addicted to, but it's bad for us.
The root of all evil.
And I kind of believe that to be true. It's asynchronous. Synchronicity makes no sense when you think about it in the real world. It's just when I talk to you, your brain doesn't freeze while I'm talking to you, and I don't freeze while I'm waiting a response. We're both processing independently of one another. That's kind of the fundamental of
Speak
communication.
for yourself.
Wait, David, what did you say?
It does depend how boring I'm being, I admit.
So this is yet another counterexample to the assertion that things are simpler. As soon as you have asynchronous messages, that's a lot more complicated than if you have synchronous messages. I don't care how you slice it. You're introducing complexity.
Is it so much more complicated, or is it just so much different to what we've been doing for past 20 years of as developers?
I think it's more complicated. I think having a sequential, I'm going to do A and then I'm going to do B, and when I get done with B, I'm going to do C, is easier to conceptualize. It's easier to implement. And if you're going to tell me that you're going to interrupt me between A and B and go off and do something else, I'm now have to do a lot of work to allow for that.
Agreed. But let's put that whole discussion in context, though, because what we're talking about with Reactive Manifesto are systems that are highly responsive, highly elastic, and highly resilient. And in order to achieve those three elements, I would maintain that it has to be asynchronous.
Yeah.
I don't think you can do that. So then, I agree for systems that don't require those aspects. With that complexity, I believe is necessary in order to achieve those aspects. If you don't need responsiveness or elasticity or high levels of scalability or that resiliency within our applications, then reactive is probably an overkill. Would you agree? Which I think supports your view about that level of complexity not being needed.
Sorry, go.
No, just to point out that I also think that a big point of complexity in transition a system from a traditional MVC architecture to a reactive architecture is the change of mind, the paradigm shift between the request reply stuff and the asynchronous, totally asynchronous stuff, and so you are reacting to events happening in the system, and not just sending and waiting for a reply. So on that, on this kind of debate, I would like to point out that maybe correct way of making the transition could be starting from the orchestration, putting something like a service compositor or composition, making a request to different services before putting the infrastructure for messaging, asynchronous messaging in place. So that's my point.
Isn't it that we are, at the moment in this debate, we are kind of having three elements, like the complexity of the system that with reactive is supposedly, according to Len, increasing. What you, Mark, just said, that maybe we don't need reactive for all the systems that we are building. So maybe there is a space where the traditional synchronous architecture is working totally fine, and something that's more reactive. And you mentioned that they're kind of a trade-off between one and the other, and maybe we can drill down those elements. Starting with what you just said, Mark. There might be, if we are talking about a highly resilient, highly responsive system with the elasticity, because obviously when you ask business, does it scale? Obviously it should scale. So if we are talking this system, I found a distinction which was referred as a Netflix point or a Google scale. Like, and then Netflix did reactive all the way down. They wrote Eric's Java and a few other libraries about reactive programming. That was the scale for reactive system. Is my system that scale? How can I answer that question? Is what I am building at the moment that scale that I will need reactive, and how can I sense it? How can I probe it that, yeah, reactive as a way of building this system is something that I was going to need, or neglecting that will kill me in the future?
Yeah. Well, so to kind of first answer that, I'd really like to clarify the difference between elasticity, what Dave was talking about in the definition, and overall scalability. Because scalability is kind of a sustained growth of requests made. I tend not to like to use users, because no matter how many users you have, they may not be doing much. You may have the same user base, and you increase some features, and those users are doing more. So I like to think about it in requests, and so we'll use requests. If you want to use users, that's fine. As the requests increase, does the system handle that increase in terms of capacity and performance? Elasticity, though, is really defined as an architectural characteristic more those extreme peaks of unexpected load that we get, whether it be through some sort of market condition or event that happens economically, whether it be what we have in the US, I'm assuming here, as Cyber Monday. Is that here? Yeah. Well, somewhat, yes. Where it is the one day where everybody buys everything because there's so many sales. And that's elasticity in its sense. Very, very hard, actually, to achieve in applications. A lot of applications simply don't need high levels of elasticity. You can achieve elasticity without being message-driven or async. For example, in microservices, we can auto-scale within orchestrators like Kubernetes, for example, that detect that load and start increasing the instances of services. That has nothing to do with messaging. However, that said, for extreme peaks, that has a certain limit. And that's where I think that message-driven asynchronicity is required and needed. I forgot your first question, Bo.
But you answered that one.
I just like talking. I didn't.
No, you actually answered that one.
And your question was?
So the other aspect, the other differentiator with that elasticity and scalability is really you can shrink as well as expand, which I think is important. I do want to go back to this idea because I'm a little bit nervous that what we're painting the picture of is that this is an architecture for big, complicated systems, and I think it's more than that. I think it goes further than that. I think I'm clearly in the minority on the panel in terms of thinking that actually there's something that's fundamentally simpler in terms of what's going on when we're talking about this. And I think that one of the reasons why we think that synchronous interactions are simpler is because that's what we've been acclimatized to. I think if we just think about these things in a different way, they're actually equally simple in very often. So certainly, as soon as you start talking about distributed systems, asynchronous systems remove an awful lot of the complexity from the problem, to my mind. Distributed systems are fundamentally significantly more complex than non-distributed systems. But as soon as you start distributing, I believe that using an asynchronous approach gives you an awful lot of leverage to make these things more simply. And so, for example, I've got my own home project, which is a reactive system that's a small system that's running on my computer at the moment, and I'm working that way because it's an easy way of developing the system that I'm trying to build.
I see Len and Christian
No,
tend to disagree.
Yes, yes, because no, just the first point is that I was referring to a learning curve, so something. I mean, the change of paradigm in the mind of developers, not just the system is mathematically less complex. And the second part is that I think that for example, a typical web application, typically single-page application, is counting on requesting and replying. It's quite rare to find a web application that receive responses, for example, from a WebSocket. It's not so common, I mean, at least in my experience. And this is one added complication in applying a reactive architecture to everyday projects, I think. I mean, there are aspects, for example, another aspect is the infrastructure. I mean, you have to add a sensible investment in infrastructure, and it could be difficult to introduce it for a common team and a common project. That's where my point.
I think there's some really interesting points in there. So first of all, you're absolutely right that the cultural environment in which you're operating this, most of us developers are not used to thinking in asynchronous patterns, and that's a problem. But I think that when you get there, it's easier. Also, the infrastructure on which we lay, HTTP is a request-response protocol, so building asynchrony on top of there is absolutely doable. And you build much nicer web UIs when you treat it as an asynchronous route and you ignore the response bit. but that's not the normal patterns that we're familiar with. So I do agree with what you're saying. But I don't think that obviates the fact that you can build more complex systems using more simpler programming techniques in many ways when you buy into this model, to my mind.
So I would like to ask my panelists a question. Can I do that?
Of course.
Is a reactive system, what part of it is infrastructure and what part of it is a system that I'm building? What should I assume from my infrastructure in order to build such a system? Which is kind of
So, do you want to go? Shall I?
Go
That's a good question, I think, and I think this is one of the reasons why I think that the asynchrony of the messaging is important. That then puts significant responsibilities onto the infrastructure. And so the infrastructure needs to, in order to get effective asynchrony and to simplify the problem rather than complicate the problem, the point of entry into a given service needs to be single-threaded. So you're not going to be handling the asynchrony in the middle of the business logic. You're going to be, the delivery needs to be idempotent. You're going to get a message once. It needs to be at some level assured it's going to be generated. So you need things like the kind of log-based replays of messages that you can kind of, and then you can do all sorts of funky things like you can kind of offline the persistence, you can do sharding at the messaging level, and all sorts of interesting things outside of the little bubbles of single-threaded business logic that are able to process these events. So so one of the common patterns for this is kind of actor patterns. So light bend and those sorts of lag arm and those sorts of technologies is one approach. We took a slightly different approach, but you have these little bubbles of logic that are inherently simple and stateful, and they're communicated via asynchronous messaging, and then you put quite a bit of smarts into them, not business level smarts, but accidental complexity smarts into the infrastructure, for sure.
So let's talk a little bit more concretely about some of these aspects, because when we talk about responsiveness versus performance, the Reactive Manifesto is really saying, how do we impact responsiveness? And to really illustrate this need for message-driven, let's say, and here's a real example, I'd like to post a comment on our website about some sort of product or service. And let's say that takes 3,000 milliseconds to post a comment, because it's all automated, so we're going through bad word checkers, a national bad word checker, our own company's bad word checker to make sure you're not saying any bad words in that comment. We're going through grammar parsers to make sure that what you're saying is not abusive. We're going through context checkers to make sure that your comment, programmatically, is about a particular product or service and not a political rant. That all takes 3 seconds. 3,000 milliseconds. Now, we're going to post a comment on the website. I'm typing it up, and all of you ready? Here we go. I'm going to hit enter. Thank you for your comment. That was a lot of dead space, and I can't believe that you wasted 3,000 milliseconds of my day. I'm a busy person. So, responsiveness is this. Now, that was synchronous calls to give you back that thank you. Let's do this with asynchronous messaging. I'm going to hit enter. Thank you for your comment. Folks, that was 25 milliseconds to post a message to an asynchronous queue. Now, behind the scenes, of course, it's now spending 25 milliseconds to get to the service, 3,000. That's responsiveness. I did nothing, everybody, to address the performance aspect of that comment service. I didn't run things in parallel. I didn't try to optimize the service. No. All I did was leverage asynchronicity. In other words, asynchronous messaging. And that's what we're talking about with responsiveness versus performance. To be able to deliver faster response to our users when we don't need information. As a matter of fact, when we do, we can still leverage this through promises and futures and do work in between that promise or future coming back. And so the point is, same thing with resiliency, and I'll finish with resiliency, is the point where resiliency is about handling errors. Well, in the spirit of reactive autonomic systems, what we do is this whole mantra of delegate, isolate, contain, and fix. This is what our human bodies do. If we catch a cold, a common cold, we don't crawl in bed for 2 weeks. Well maybe some of us do. Most of us won't crawl in bed for 2 weeks. Most of us will have the sniffles and a red nose and carry Kleenex around, but we'll still go to work and spread that cold everywhere. The point is our bodies don't shut down. It isolates. It contains that error and then goes to fix it. The same thing. Let's get concrete about this. Resiliency, how does that impact responsiveness? Because if I get an error on some sort of request and I try to programmatically figure out what that error is, what am I not doing? I'm not getting the next request or getting that next trade. And so the point is, if an error occurs, delegate it right over to Dave and move on. Next. That's responsiveness, everybody. However, Dave, in the meanwhile, through asynchronicity, I send it over to Dave and say, here, you work on this. I don't need a response. You just work on it. Now, I'm available right then and there for the next request. That's how that elasticity, the eye candy associated with reactive, you can tell I kind of like this stuff. That arrow goes back up to responsive to say, yeah, you can fix an error, but did it impact responsiveness? These are great examples. We already talked about elasticity, but these are great examples of why event-driven, or I should say message-driven, is required, because we can't do that through synchronous calls.
So does he believe what he's saying?
No. Like I said, I just like to talk.
So one more thing to add to that, because I think Mark's description was great, but one more thing to add to that is my field is in seriously high-performance systems, so this is also the way of writing the most high-performance systems. And so the 99th point, how many ever 90 you like percentile of interactions are going to be responded more quickly in this scenario. The fact is that I can send a message to Mark and say, do this thing, And at some point, I'm probably going to get a response back, but that point doesn't matter whether it's microseconds or nanoseconds or days or weeks. I am not tied to that, to the timeliness of that response, and that gives me flexibility too, to both be very high performance but also very resilient.
So what I'm hearing, so there's a question as to what kind of systems does resilience require resilience. And what I'm hearing is that it's high performance systems. It's high performance and high load systems.
No.
So let me use one of Owen's example. Okay, so I have a control system that runs off a sensor that's embedded in my thermostat. Okay, how am I going to scale my thermostat? You know, and it works at a certain speed. How do I make it faster?
That's getting back to my point, is that that's not the only dimension. They're also simpler. So the criteria is not high performance. High performance is one of the effects that you can gain, but they are distributed. And as soon as you're talking about distributed systems, these sorts of systems are simpler versions. Because as soon as you're talking about a distributed system, you've then got to worry about all of the ways in which it can screw up. And any sort of distributed system. So I think that the point at which you would genuinely say, is this a sensible architecture? Maybe if you've got a single process system. But so why would you do this kind of architecture then? You probably wouldn't. But any other kind of system. So let's just be clear. This is the way that our processors work. So at the core of a modern processor, it's a it's an asynchronous message passing driven process, and it uses protocols to manage the data. This is a fractal thing. So this isn't just about big, cloud scale systems. This is also about there's something fundamental here. There's something important, and I think getting. I know I keep bringing it back to the simplicity of the programming model, but I think that's very important.
But that's because all of the complexity is hidden somewhere.
Exactly, Len. Yes. So, yes. It's developer simplicity
Yes.
and architectural complexity.
Yes.
Will we concur?
Yeah,
I think that's,
agree with.
yes. So wow, we actually agreed on the debate. This is awesome. So it is simple, but it's complex.
It's simple, but it ain't easy.
No, there you go. Yes.
And it depends on having an infrastructure that supports that complexity.
Yeah, I just want to reinforce the point that it is developer simplicity and architectural complexity. That is always true in any distributed system, and this is a simpler architectural complexity as well.
What you describe is that you can handle high throughput, high volume, but what you mentioned, but we didn't cover, like we didn't drill it down, you can also scale down. Yes. So ultimately, if you have low volume, you can have better hardware utilization. You don't have to this CPU graphs that are no more than 5%, and your CPUs are just doing nothing. You can, or you can't.
But what happens when you hide complexity like that, and Ian could give a lot of examples about distributed systems, is that every now and again it leaks through, and there's a problem, and you have to deal with it, which means that you have to understand the complexity, and that's not easy.
Right. So let's use an example of that, because my example of that comment illustrated the responsiveness. But what's the problem with my example is the fact that when I hit enter, thank you for your comment, I got a response in 25 milliseconds. What's my assumption? My assumption is that comment got posted on the website, or that trade got placed and is now being executed with a broker. That's the problem. That's the hidden complexity. Yes. And that's where certain reactive architecture patterns, such as the workflow event pattern, are able behind the scenes to capture that through delegation, isolation, containment. Let's say I do put a bad word in. Let's use a real example. I put a bad word in, a bad word. I'm not going to say any bad words, but I mean a bad word that you shouldn't use. I put that in the comment. Thank you for your comment. What's the very first thing that's going to happen, everybody? That comment service is going to say, nope, not allowed. And so delegate, isolate that problem. I send it to a queue. Dave picks it up. This is the workflow event pattern when we start talking about patterns of reactive architecture. Dave gets that error and he says, I see the problem. Mark just put a bad word in there. Well, why don't I try to program? See, I can't get back to Mark, so why don't I try to programmatically fix that by putting little asterisks, stars, on that bad word? And then he resubmits it back up to that comment service. And all of a sudden the comment service says, well, there's a lot of stars, but there's no bad words. I'll accept this. Posted. As far as I know, that error never occurred. I see asterisks and it's like, well, that's pretty cool. I'd rather have the bad word, but that's pretty cool. That's an example of complexity. It's necessary with the reactive architecture, because if we're going to be self-healing, and that's another illustration of self-healing systems, instead of sending it back saying, no bad words allowed, no, we try to programmatically fix it. That's resiliency.
Okay, so let me carry through with that example.
Okay.
So you take your thing with the stars and you send it to a grammar checker. And the grammar checker says, oh, what the hell are these stars? I'm sorry, bad
Oh,
word.
bad word. All right. No, no.
What are these stars doing? Probably what he meant was, and it makes up a word. And it puts it in.
Now,
and now it's self-healing, it's resilient, and it doesn't have any connection at all to what you wanted to say.
and I think that's a good illustration of the complexity that's hidden behind the simplicity that Dave's talking about with reactive architecture. Yes, it solves all these problems with trade-offs, and I can't wait till we start talking about those many trade-offs, but one of them we're already talking about is this complexity, and I would concur. There is hidden complexity when we try to achieve this level of elasticity, resiliency, and responsiveness together.
I think that's kind of interesting. Also, going back to the stuff that Len was talking about earlier, in terms of the kind of the social framework in which you're going to develop systems like this. I have to confess that the system that I have most experience in building this exchange using these techniques was a relatively small team, so it was fairly easy for us to say, I've just implemented this, we're going to put crosses in, so if you want to handle the grammar checker, you need to think about that. So it's easy to have that kind of communication. If you're working at Google scale, maybe that's a more difficult conversation and a little bit more fragile at that scale.
I think we've all had experience with spell checkers and the words that they substitute may or may not have any connection to what your meaning was, and I see that potentially happening quite a bit.
But in terms of a resilient system, you could imagine understanding that a line of asterisks is a special case and that you're not going to correct those or whatever else.
Well,
all right, so I misspelled it. It wasn't a line of accident. I just misspelled.
But we are talking about yet another trade-off, because one of the things that the Reactive Manifesto or reactive architecture, let's stick with reactive architecture, doesn't support is what Len is talking about, which is really that data integrity and that data consistency. Those are other trade-offs that happen to occur with asynchronous processing.
That's certainly one of the trade-offs that you undertake. I was having this debate with Ian over breakfast this morning. There are only a few things in computer science that are genuinely hard. There's concurrency, there's coupling, and he added, which I think is versions of concurrency and coupling, but he also added data consistency. And everything else in computer science is relatively easy, but those three are bloody hard.
Well, actually, I do need to correct you on this, because there are only two hard things in computer science. The first is cache invalidation. The second is naming things. Oh, and the third is off by one errors.
That's a classic one, right?
Baba boom.
I stole the joke.
But I couldn't help myself.
But as we get towards as we're drilling down the trade-offs, you mentioned one that is like pushing the complexity that we had inherently in our systems to the infrastructure. You can discuss whether infrastructure people know their job because they've been there for years and they might know better than EJB, for example, from our past, or Cobra, which was already mentioned today. Then you have this awareness of business processes, because if you orchestrate those or you do those flows, you have to understand what are the business trade-offs, not only technical trade-offs of not handling the message, but how would actually business respond to not having this comment posted for a while, and will it be particularly relevant to their business or not. Are there any other, like, because we tackled a lot of benefits. What any other?
Let me put on my educator's hat. Ian isn't here, or I'd borrow his hat. At what point do we start to teach people about asynchronous?
Now.
I think
mean, at age 5, at age 10, at age 15?
I think it depends.
age 5.
Well, in computer programming, I think it depends, because now I know a whole bunch of people who started their career with JavaScript and the browser, and they don't really have a concept of synchronicity, because all they know and all they learned so far was JavaScript, browser, and Node.js. Inherently, all the way down asynchronous. So I think it very much depends where we are all the lines in here.
Well, this is what Christian was just talking about. No, about just the mindset change. It is a paradigm shift. When we went from procedural code in C way back when to object-oriented back in '93 or whenever that was with C++, that was inherently a paradigm shift. In other words, that different way of thinking of saying, well, who's going to call this method? Well, don't worry about that. It's like, no, I need to worry about it. I need to visualize this flow. No, don't worry about it. Somebody will call it later. That was a paradigm shift. And I think what you were referring to, if you could talk a little more on that, was this paradigm shift of thinking in reactive terms. Yeah. Can you talk more about that?
Yes, I was just pointing out, well, a little example. For example, I think anyone in this room is able to use a library. A library, typically you invoke some method, something that returns a value or something. So that's why we are so used to request a reply, and we just translated the same concept into the protocol. For example, the HTTP protocol is inherently synchronous, and to the architectures. For example, I've seen personally many microservice architectures based upon HTTP requests between services. So the idea is that it's not a library, it's just another service acting as a library. That's a big problem for me, and that's the paradigm shift that we have to do. I mean, it's not a library, it's just another service which is subscripted to events I emit. That's the point for me.
But when I talk about the simplicity and the fact, I completely accept what you're describing. But when I think about the simplicity, if we're making a synchronous call for any purpose, we're going to call and we want some answer, and and we are tied in time in order to be able to achieve that. But if we just make the call and then sometime later we get an answer back through another message, that's the same. It's the same kind of thing. So as long as I divide up my logic, I have to confess I'm not a big fan of the reactive programming style where I mix all of these things together. I just want an input, and I just want to send a message, and I'm going to get another message which tells me the results, the answer, sometime later, and I'll process that when I get that.
But in the meantime, you have to go and do something else, or it's synchronous, and going and doing something else gets complicated.
Well, why? Because I just respond to another message.
Because of why is it complicated? It's complicated because of the management of state.
This gets into another one of these patterns that Mark's been talking about. So one of the very common patterns is that what is effectively you treat the state of the system as a little state machine. Each message comes in and modifies the state. So let's say I'm writing a piece of code that's going to order a book. So I have a message coming in saying order the book, and then I've got to go to the inventory service to actually check that there's really a book available to order. So I'm going to modify the state of my book to say it's in an ordering state, and then I'm going to send a message saying, are there any in the warehouse? And then sometime later it's going to come back and say, and it's going to change the state of the book to ordered.
And in the meantime, I canceled the order.
Yeah, so then you cancel the order.
Now you get into compensation
and consistency.
And consistency, you're getting into a lot of complicated issues.
Well, but they're all bits of business logic that are actually relatively straightforward. So they're just
Compensation is not relatively straightforward.
Let's not talk about compensation. It's just, how about this? It doesn't exist in distributed systems. Well, there's
What doesn't?
compensation.
Sure it does.
Oh, it's the worst thing you could possibly do, Len.
God almighty. I made an order, I put it in there, it's now 6 months later, I'm tired of waiting for my order, I cancel the thing, I want my money back, I mean, and you've gone ahead and spent it, and maybe you're even bankrupt, you know, I mean, life gets complicated.
so it's a business problem rather than a technical problem. So you can just say, tell me the list of all of the books that are ordered and haven't been fulfilled in the last week, and then you can decide what to do with it. It's a business problem. So it's a problem in the problem domain. It's not a technical problem. So you've moved it out of the technical regime and put it into the problem
However,
domain. That's a good thing.
To Len's point, though,
Thank you.
it adds complexity to the developer, because now, although I have simple constructs, I am adding a lot more code to address these issues we're talking about. Now, granted, I'm still with you, by the way, Dave, on your simplicity thing, because I do think the constructs that we use as developers, especially when we just create observables and subscribe to those, is, I think, a fairly simple model from a developer standpoint. However, I do think that now we're starting to talk about this inherent complexity, because somebody has to code all these things we're talking about. And that's a lot of extra work.
It's not extra work. It's different work. I think that what you've done is that you move the complexity out of the regime of accidental complexity and into the realm of essential complexity. So you've put this into the problem domain, but that's the trade-off. The trade-off is, if you've got a synchronous call in a distributed system, you've now got to cope with all the conditions. What if that service wasn't there? What if it's gone down? What if you've lost a message? What if the message got lost in return? And all of those sorts of problems, which adds to a whole different layer of complexity. You get rid of all of those, you move all of those outside of the bubble, and yes, that comes at the cost of thinking about the domain a little bit more differently.
As long as you don't ask me to code the orchestrator, I'm perfectly happy.
So, Jakub, you asked about some of the other trade-offs, kind of associated with this, because there are. I mean, reactive architecture is extremely powerful, but when it's a sharp tool, so use it wisely. But the point is, there are other aspects, because it does require asynchronicity. We've got loss of workflow control. So what you're talking about with this synchronous kind of step 1, step 2, step 3 is very controlled. I know exactly what's happening. But when we start moving into reactive architectures with asynchronicity, I really don't have control over that workflow anymore. I don't have state anymore. Len, you were talking about state. I don't really have state. I don't have deterministic workflows anymore. Now, these are all very powerful features, but they're also trade-offs. Data integrity, data consistency. When is the data going to be consistent? Eventually. Well, when?
Just wait.
It's the only word you can come up with. I mean, we don't know how long, because we don't know what error handling is occurring. We don't know what's scaling or what's being elastic. And so these are the other trade-offs in my mind about that, is really how's this one? When does the business transaction actually end? I'm going to do a catalog checkout. I'm going to buy that book, Len. I'm going to buy your book.
Thank you.
I'm going to buy a second copy of it. How's that? Is it still available?
Yes.
Okay, good. So I'm going to buy a second copy of Len's book. Everything's async and very reactive, but when is that purchase actually completed? Does anybody know?
The electronic copy or the physical copy?
Oh, the physical copy.
Then I don't know.
Then I don't know. Yeah. And so these are the trade-offs, I think, associated with adding this kind of power or capability to our architectures.
So let me tell you what this is reminding me of, and this is an old man's comment. So it used to be that there were things called rule engines, and you had a rule engine that essentially ran off a blackboard, which is the kind of thing that you were talking about. And the rule engine approach ended up not working because of time and performance and complexity. And so what you're envisioning is essentially a kind of rule engine. Now it's not, it's not the traditional rule engine that people had, but it's having a blackboard that maintains.
Let's just be clear for a minute. So we're not talking about this as a theoretical exercise. These are real systems.
These are, yeah.
And they are faster and you're able to build, to my mind, more robust, more complicated.
So what I'm saying is that there are a certain set of systems for which this makes sense, and there are a sufficient number of complexities that show up to the developer that after a while the trade-off is this the kind of system where I want to make that kind of investment?
That's not been my experience. My experience is that this simplifies the picture for the developer, because essentially you're able to, given the infrastructure, so we built the infrastructure too, but given the infrastructure, then as far as, for normal day-to-day development, you are focused only in the problem domain. You're focused only in what's...
Can we make a small full stop in here, because you won't agree, and that's great. That's great. As we are getting slightly toward lunch, I treat it as a good opportunity to ask for a question, if there are any. If not, we can continue through our whole lunch, probably.
I do appreciate that the previous panel was a discussion. This is a debate.
Oh yeah, this is definitely.
There's one or two, quite a few questions. Please raise your hands.
Hey. Sorry about that. I want to ask something very specific on mobile applications. Because we are talking about reactive patterns, what about the complexity of combining reactive pattern with other ones? For example, on Android, for example, if we are working with Reg Java or something like that, CPS or coroutines, even coroutines, do you think it's possible to do a wrapper about these libraries, about these patterns? Just because in Len's presentations, he said software have to be modifiable as a principle. So do you think it's a good idea to do a wrapper about the reactive patterns?
So if I'm understanding your question correctly, you're referring to some of the frameworks that are used with Reactive and how those work in conjunction with other patterns and stuff. I think in my experience, a lot of the frameworks that we can use, RxJava, which you mentioned, Akka framework for Java, Meteor, Elm, Lightbend, all of these are good, fast ways of implementing the Scala programming language. As a matter of fact, RE Scala. I thought I considered Scala a reactive language because of its actor model, but now we have RE Scala, capital R, capital E Scala. Let's make a reactive programming language more reactive. It just adds some of the stuff we're talking about. I think my opinion and experience is that it helps us facilitate the implementation of these patterns in any kind of variety of architecture. But again, I maintain that these are really orthogonal to the patterns themselves. They're implementations of the pattern. For example, RxJava or Akka or Scala, and take any of these that have a Microsoft P, any of these actor models really facilitate the supervisor-consumer pattern of reactive architecture, which is maintaining that level of elasticity, those peaks and valleys of requests, while maintaining responsiveness. And so how long does a request take? 200 milliseconds. Is that for one user? Yeah. These frameworks, through the actor models and mailboxes, allow us to do 100 concurrent requests. How long does that take? 100 milliseconds. And that's what reactive is about. So I think they're really implementations, or ways, not implementations of the patterns. Let me rephrase that because that's important. They're ways of implementing some of the patterns we're talking about in reactive. They're not necessarily implementations of reactive patterns. So, yeah, but they are very helpful. But I want to just say one last thing about your question, because this is super important. Reactive architecture and implementing some of the patterns of reactive architecture do not require these frameworks. They do not require these languages. In many cases, I simply use RabbitMQ with Java or RabbitMQ in C#, and I can be just as reactive if you're using RxJava or Microsoft P. Yeah.
There was one other question from a person in a green t-shirt, I think.
Boy, you're getting lots of exercise.
Hi. Well, first of all, thank you for the discussion panel. It was amazing. I have here many notes. But I want to go back to the metaphor about hiding complexity. When you want to hide something, then first you need the object that you want to hide. Then you need a group of people that you want to hide that object from. And then you need a person that is the one that is hiding the object. So even though that you're hiding the complexity, someone in the company has to hide it. So that person will know that the complexity is still there. And then we are moving complexity from one group of people, which are developers, to another group of people that I don't know. And my question is, who is responsible of hiding and managing this complexity once that is hid?
So I think that one answer to that question, if you're looking at getting some product to support the development of this kind of approach, is that the product vendor is going to hide some of that complexity from you. So you don't need to understand the details of building an assured delivery asynchronous messaging system in order to be able to take advantage of those properties. You need to understand the implications, which I think is the stuff that Len's talking about, and I think that's clearly important. So you need, this is a software architecture conference. You need to understand the architectural compromises that you're making as a result of some of these choices, and understand how it fits into your problem domain. So that's, the team, while it's thinking about these little bits of business logic, need to have that in the back of their head about what this means, and that kind of leads you to worry about these issues of data consistency and those sorts of things. But I think in principle you don't really need to understand the nitty-gritty detail of how all of those things level at fine-grained detail. So when we did, so we were one of the early versions of this kind of system when we built our exchange, and so we built the infrastructure from the ground up in order to facilitate this. So we did have people on the team that understood this at every level, and so that's probably a special case. But there are lots of people building very effective, successful systems with off-the-shelf versions of infrastructure. The Lightbend stuff is probably the most widely used one that I'm familiar with, but there are many more coming, RabbitMQ and many others. There are many more in development of these sorts of frameworks that take some of that need to understand the accidental complexity aspects of the problem away from us, and deliver those behaviors to us so we can focus on the essential complexity of the problem.
I think you've pointed to one issue, I would say, within the global scope of reactive architecture. I think some of the patterns, like the very common ones, like supervisor consumer, and to, if you see loads, spin up more services or spin up more receivers, whether a micro or macro standpoint, is usually contained within your domain, and so that's not usually an issue. Back pressure is, because if I'm applying back pressure to an external system, or let me rephrase that, if I detect an external system that I'm responsible, that I'm dependent on, is failing, I can actually apply back pressure to other kinds of systems, let's say slow down trades or something. That does require this coordination between multiple departments, multiple teams, multiple divisions sometimes, as well as, I think the workflow event pattern of kind of handling the resiliency aspect is also kind of more self-contained. But you're pointing to one of the complex issues associated with that. And it is hard. It is hard because you are absolutely correct in your observation. We keep moving the complexity further and further down, and who's responsible for it? Ultimately, you need knowledge, as Len was saying, all of a sudden, of some of these patterns do require knowledge of all the systems. If I'm going to be elastic and I'm going to scale up my services, are you scaling up yours as well? Because I'm dependent on you, and I don't have responsibility or access to your service. So I spin mine up, And I create 40 instances to be able to handle that peak load, and you've got 2 up there. Boom, it's going to fail. And so, yeah, these are the complexities involved and the synchronization that's required between the domains, and that's difficult. As a matter of fact, in our workshop yesterday, we had quite a rabbit hole with this kind of discussion about the complexities of distributed architecture in general and tying everything together through these sagas and workflows and asynchronous behaviors between them. So, yeah, it's a good observation, and it is one of the complexities.
Any other questions? Oh, there is. That's going to be a long run. Just shout.
The next one has to be from the very far left-hand corner in the back, okay?
Hi. First of all, thank you for the debate. Very, very interesting. You were talking a lot about how reactive architecture simplifies the life of a developer. I can see this simplification when you are developing things, but what happens when you have to debug something? Something failed. Maybe you can place an order. In a classic system, I can say, okay, this button is sending this message to service A, this one to service B, this one to service C, and this one is failing. But with this event, when we are sending a lot of messages over the different services, how do we know where is the source? How do we know where is the problem?
Len alluded to this earlier, I think, in terms of well, one of the accidental complexities that you can externalize to some degree is that observability, because the infrastructure knows where stuff is going and where it's being consumed, and so there's you've got a log of messages that you can kind of replay and reconstitute state in different parts in the architecture and all of those sorts of things. So you can instrument that, so you can kind of tell that sort of thing external to the system. So, for example, we had a network tap in our trading system that would identify packets coming in across the network, and it would maintain a correlation of interactions. And so we could build a picture, and we could kind of, for us, we did use it as a performance thing. So we could measure performance at different parts of the message flow. It's not simple, it's complicated when you start thinking about those sorts of things, and you may need to dig into sort of the more technical complexities, but it allows you to do that separate to the business logic, which I think that separation of concerns is the thing, as you can probably tell, that I really value.
Right, and to kind of follow up with that separation of concerns, generally in these cases, it's the same kind of thing: delegate, isolate, contain, repair. And so the point being that if I'm sending a payment, I just bought Len's book twice over. I need to apply the payment. I just send a message. If that payment can't be applied, it's not my responsibility. So generally in reactive kinds of systems, we have these silos where if you're, let's say that you're the payment service, I send a message to you. I'm kind of done. You let me know when the payment's applied. All of a sudden, my credit card expired, which happens all the time, by the way. And so what happens? As a payment service, you're going to say, well, yeah. So the payment service is going to send a message to a notification service to say, email the person and tell them to update the credit card in their wallet. The wallet service is going to send a broadcast out saying, credit card's been updated. The payment service listens on that, applies the payment, sends a message back. My point is, everywhere along the chain, we have self-contained error handling. We don't delegate that to anybody else. And so that's usually where we don't have that workflow piece. Again, now I don't have control over the workflow. As order processing, I don't know, I did my part. I've got an order saved here. It's under ordered status, but not completed yet. I don't know. Somebody's going to let me know eventually. And it is a different way of thinking, because as developers, think about this. You want a guarantee of everything. You don't want any edge cases. And in distributed architecture, they exist, and we can't plug every hole. So we start to look at these trade-offs and say, well, I want every hole plugged. Which is more important? To plug every single hole and address every single use case to ensure 100% data integrity, or have extremely high responsiveness, performance, agility, testability, availability, elasticity. Which one's more important? Because like CAP theorem, you can't have both. Pick one, and that's what ends up happening a lot. That's what Christian was talking about with that mind change kind of thing. It's hard to say, so this is not a guarantee? No. It's not. But it's usually self-containment is the answer.
Any others, or we are getting for lunch? There's
Besides George.
there's high profile question.
Oh, here we go.
Hi there. First, do any of you sell any books?
Please don't get there.
The,
yeah.
I sold 2 copies.
Eventually.
I haven't paid for them yet.
I want to echo what the other guy said. This has been really interesting, and I think the examples you brought up are very good at highlighting the challenges and the opportunities here. And in the discussion about simplicity, I don't think anyone is suggesting that there isn't a good place for such systems, and that there's a lot of know-how you guys are bringing about this. So when I still continue to question this idea of simplicity, I want to connect this with the talk that I did at the beginning, right? And there was the source code for the traffic light, which was incredibly simple from one way of looking at it, right? You know, it's turn it on green in 30 seconds one way and then 15 seconds the other way. The challenge I have with code like that, that's simple in its expression, is that it's the tip of the iceberg of the theory that lives behind it that lets you understand why 30 and 15 were the right thing. And so when I hear it's an incredibly simple chunk of code that says, put this event in the queue, you're done in 25 milliseconds, I'm like, yes, A+. I completely understand that code enqueued that event. But when you elaborate the example, it seems like in order to understand if that was the right thing to do, I need to have a lot of knowledge. I need to be able to stitch together a big theory that says there's no path through this graph of event handling that drops this on the ground. And that becomes, it seems to me, there is a lot of complexity there that is not apparent in how simple the little bit of code that does any individual task is.
Isn't it like what you said, that it's not necessarily a technical problem? It's a domain problem.
Yes. Yes.
Actually, so if the original straw man, this is the code I would have written. Start transaction. No, I'm not saying that's the right way to do it for high scalability or throughput. Okay, but this is the comparison, right? Like this is my old-fashioned code that would say start transaction, do thing 1, do thing 2, do thing 3. Oops, it barfed. Okay, roll back the transaction, right? That was our synchronous model with relational databases, and it was easy to write. It just didn't have the properties you're looking for. Mm-hmm. So the only thing I'm pushing on is by pushing those problems, as you say, into the problem domain, and I agree that that's one way of doing it, it still has complexity. You're creating complexity that was not part of the original problem that had start transaction, do all these things, if successful, commit.
So I want to talk in kind of general terms without the example. First of all, is that subjectively, my observation is that people that adopt this approach for building real systems, the most common thing that they say is that they're surprised by how simple the systems have become. So they love the resilience, they like how fast it is, but it seems like a simpler model. That's my observation too. That's what I found, and I confess, it's very hard to do this without sort of getting down and showing code examples and sort of saying, look, because you could write this instead of this and so on. So in your transactional boundary, it kind of depends where you draw the line. So if it's a transaction and it's I need those 3 steps to have happened, they're probably going to happen in one service, so they're going to happen on one thread. I'm going to have a message that does that thing. So the transactional boundary is the scope of the processing of that single message. If we're talking about a distributed transaction across a number of different services, different way of cutting the cake, and that's a different problem. And there isn't a nice way of doing distributed transactions. Certainly, distributed transactions, as were implemented in, Corba or EJB or all those sorts of things, are very, very ugly things. And so you need consensus protocols and things like that to apply to achieve that. And again, if you want to go in that direction, you can kind of think about that, and you can kind of push that out, some of those concerns into the infrastructure. So you can build consensus protocols and stuff like that into the infrastructure. But the actual problem of, do I need to do this thing and make sure that they all happen together, is a problem of the application. And you can build that into your messaging structure as long as you've got all of these properties of of some level of assured delivery, once only, and all that kind of stuff as part of the background.
There were a lot of hands up when we first started this debate. It's not a panel, by the way; it's a debate. That were using or understood reactive, whether it be using reactive framework, whether using React.js, whichever it be. I'm curious of a show of hands of how many of you, and be honest, how many of you have found those programming models easier as a developer?
Just me.
I think it's just you, Dave. Okay, yes.
Isn't it like with the so-called first law of Martin Odersky? The moment you understand what monad is, you cannot describe it to anybody, and we have a first law of Fairley. If there's no other questions, I think we can make a full stop here, and lunch is waiting for us. Thank you very much, gentlemen. That was a wonderful discussion.